And his rate of progress is determined not only by his qualities as a craftsman, but also by the qualities of the tools at his command. And so, impelled by the endless hope that his works may excel and endure, man's quest on earth has always been for ever more reliable and durable tools to match his persistent and growing ambition to produce excellent results. Anything can be a tool: a wheel, shaft, or shoe, a ring, gear, or fork. Man through the ages has turned for his most critically important tools toward what is both the oldest known and among the most modern and advanced of all metal forming methods: the process known as forging. To forge is to hammer or to squeeze a metal progressively into a prescribed shape. This movement of the metal in a prescribed manner refines and elongates the grain of the metal, producing maximum strength and fatigue resistance for that material. Whatever the part, it is given greatest strength at points of greatest stress by controlling grain flow in developing the forging. The result is a part with unexcelled strength-to-weight ratio. As the internal structure of the piece is refined and oriented, the shape is being produced. And as the shape is produced, added strength, structural integrity, impact, and fatigue resistance, and other improved mechanical properties are developed. Forging and the heat treatment which may follow it enable the fullest capabilities of a material to be realized. A properly designed forging provides maximum structural integrity, reliability, and durability by virtue of the unique working it has received. Almost any metal can be forged. It usually starts with billets and bars, but sometimes starts with ingots or metal powder, and proceeds in a variety of ways to produce the necessary metal movement. Forging is accomplished by forcing the material into the confines of the carefully designed die cavity. Some forgings are hammered, and some are squeezed. The main difference between hammering and squeezing is the speed with which the pressure is applied. There are materials which are forged best by sharp hammer-like blows, and other materials which resist rapid reshaping and must be forged with slowly applied force. Many parts can be produced either way, at the option of the forging designer, who also has at his disposal several supplementary means of forging, which provide him with ways of achieving desired shapes and configurations. For example, shaping metal between rolls may be a forging operation. So is twisting. And so is bending. Used before or after basic forging operations, such supplemental means make it possible to forge more complex configurations. There are three general types of closed die forging designs, distinguished mainly by their degree of dimensional sophistication, as illustrated by these three versions of a typical channel section. These are no draft, commercial, and blocker type forging designs. Most sophisticated of forgings is the no draft or close tolerance type, which is closest to a fully completed part, needing little or no machining to make it ready for assembly. Next are those forgings whose configurations are less sophisticated, generally calling for some subsequent machining to make them functional. Commonest of forgings, they are called commercial designs. Commercial type forgings have slightly tapered rather than vertical sidewalls. This is only enough to free the finished piece from the dies, and the angle usually ranges from 3 to 7 degrees. Some surfaces of many commercial forgings are ultimately used as forged. Some commercial forgings are further refined by coining, which brings the forging closer to the dimensions of the ultimate part. The least precise of closed die forgings are the blocker type designs. Blocker type designs are used when the characteristics of forgings are wanted in the finished parts, but time does not permit or the quantity does not warrant the sinking of more complex dies. As their name implies, they are blocked out shapes which roughly approximate the form of the ultimate part. No draft, commercial, and blocker type. These are the distinctive types of closed die forging designs. Another distinct type of forging is the open die or flat die forging, which uses the simplest dies and produces the least precise configuration. For some applications, it meets a real need. The successive steps required to produce a forging may be performed in various ways, depending upon the requirements of the finished part. Here are some examples of forging production. A board hammer, steam hammer, airlift hammer, mechanical press, horizontal forging machine or upsetter, hydraulic press, high energy rate machine, an impactor, heat treatment, when required to complete the development of optimum properties, is frequently provided by the forging's producer, who is also equipped to clean the parts. The closed die forging process assures a high degree of structural integrity and dimensional uniformity, part after part, and offers assurance that inspection requirements can be minimized. The internal uniformity of forgings provides consistent machinability and lends itself to consistently trouble-free, high-speed processing. To help a designer determine when a forging should be used, he can review some of the uses to which forgings are already being put and why. For example, forgings are found at vital points of automobiles. They provide safety in a high-speed world. Also on bulldozers. Earth-moving equipment. On hard-working equipment like this hydraulic hammer. And forklifts. Forgings fill critical requirements in railway applications. Mining equipment. Trench diggers. Valve and pressure fittings. Tractors. Trucks. Aircraft, and missiles. A product designer seeking maximum engineering value in designing a part which is relatively lighter in weight, less bulky, stronger, more shock and fatigue resistant, more easily machined and heat treated, weldable, and economical, can make no better move than to call in a qualified forging engineer. The help of experts with broad forging experience is essential because forging is a fine blend of art and science, and both theory and practice are required for maximum effectiveness. They will consider the functional requirements for the part, including stresses and operating environment. The overall assembly, perhaps thinking of possible economies of integrating 2 or more parts into a single forging. How many of these parts will be needed? How soon and over what period of time? They will consider the fillet and corner radii and the thickness, depth, and draft angles of webs, ribs, or flanges. Going too far one way can make a forging needlessly expensive to produce. Going too far the other way can make it bulkier and heavier than it needs to be. They will consider the properties the part must have to determine the proper forging and heat treatment operations. The corrosion problems the part may experience. Its operating temperatures and the temperature changes it must undergo. The selection of the metal or alloy, the machining methods and locating points. They will have in mind greater economy coupled with greater reliability and effectiveness, excellence of design, appropriateness of material, and the fullest possible use of the characteristics forging can bring to any assembly. The art of forging is being augmented by the science of forging at an increasingly rapid rate, especially in the fields of research, development, and quality control. Better forging materials and new ways of forging for optimum properties and soundness are being developed by comprehensive programs. The advance is continual, using a variety of techniques. Improved types of corrosion, impact, and magnetic permeability tests. Ultrasonic, radiographic, and dye-penetrant inspection methods. Electron microscopy. Spectrographic analysis. The complete range of modern laboratory instrumentation. Forging capabilities and knowledge have expanded immensely in recent years, and this learning is being advanced at an accelerating rate. Steady advance in forging technology continually transforms difficult designs into practical production. The vision and the courage to go ahead are the only observable limitations on the growth, refinement, and enlargement of the forging process. There was a time, for example, when the only way to transfer a forging from one operation to another was by hand. Today, this is done mechanically, when the quantities involved make it economically feasible, or when the weight involved makes it humanly desirable. There was a time not long ago when forgings this large could not be made because there was no equipment large enough to forge them. There was a time when a configuration like this was considered difficult to forge because the metal would cool too rapidly for it to be forced through such thin webs and fill the rim. Today, such configurations are increasingly available. There was a time when copper and its alloys, and later carbon and low alloy steels, were about the only metals considered forgeable. Today, the list of metals forged is long and growing continuously, including a large number of steel alloys and the mar-aging steels, along with aluminum, magnesium, titanium, tungsten, beryllium, columbium, molybdenum, zirconium, hafnium, and others. Carbon and low alloy steels have long been the workhorse materials for forgings, and they meet a variety of service requirements. These are the forgings that have helped to empower humanity, to farm its crops, to manufacture its products, to build its highways, and to put people and their goods on wheels. The carbon and low alloy steel products of the forging industry are found at the vital points of almost all modern conveyances and machines. The higher alloys and non-ferrous metals with higher strength-to-weight ratios and with such properties as resistance to corrosion, high strength at high temperatures, or special reactive, non-magnetic or electrical properties are the ones whose forgings have helped put us into space. Many product designers, however, are not trying to shoot the moon. They are simply shooting for lighter weight, less bulky, stronger, more shock and fatigue resistant, more easily machined and heat treated, and surely more reliable components to match their desires for excellent results.